Hi everyone, welcome to Driving Change. It's going to be a talk on our Vulkanising of Mad Max. It was a game that came out in 2016, I think. So firstly, here we are. We're from Feral Interactive. We're a Mac, Linux, and mobile games publisher and porter. These days, that means that about 98% of our ports are all done in-house. I used to be doing OpenGL and now moving towards Metal and Vulkan. We've ported maybe all over 100 Mac games and now 15 to Linux, which is what we'll be focusing on today. My name is Mark DeLucio. I'm a Linux developer. That's generalist kind of thing, everything from graphics to system APIs. And I act as Linux group lead, which just means I spend some of my time organizing Linux developers. And Alex Smith is here as well, who's going to be chatting a bit later. He's also a Linux developer, but he's currently acting as the lead Vulkan developer and did most of the work on the Mad Max Vulkan port. So firstly, I just want to run through why we chose Vulkan. I think Tom covered some of these things in his quick introduction. But basically, for us, it's cross-platform. We really need cross-platform APIs. Obviously, we're porting to many platforms. That's why we use SDL2 on Linux, why we used OpenGL in the past. So for us, it's cross-platform. I say ish because it only covers two of the platforms, Linux and mobile. But that's brilliant for us. Obviously, as a game developer, we're always in need of lower-level control. With OpenGL, we're pushing the boundaries using as many up-to-date extensions as we can, using things that aren't even in GL 4.5. So we've been searching for something for a while, and then Vulkan comes along, and you're pretty happy with that. And really, explicit APIs are the future for the low-level work we do. We always work in the graphics engine layer, basically. And I say DX12 there because obviously we port from Windows to Linux and Mac and everything else. So we're porting from Windows APIs. Generally, the graphics engine intermediary layer is going to be tailored towards them, and DX12 was coming out, you wouldn't really be able to do GL on top of that, so we have to do Vulkan. So it really is the only option, but it is a fitting one. Don't get me wrong. And these are just some things that we think are really beneficial. Obviously, it's not part of the Vulkan driver, but the shared GLSL frontend using GL slang is a huge boon. That shared a lot of code base and saved us a ton of time, and I think it would do you as well if you haven't moved over yet. And I say HLSL there because some people are still using it, obviously, and it's now, I think, GL slang has a front end for that now, certified. The documentation for Vulkan is excellent. Anyone here who writes it has done a very good job. It's probably the best, well, for me at least, the best documentation for any graphics API out there. You can just read the documentation, the specification to learn Vulkan. Sometimes it's great. And for us, the validation layers and conformance tests are huge bonuses. Validation layers obviously finding bugs that way before they actually manifest. And the conformance tests obviously finding bugs in the driver way before they manifest, which is a massive bonus because that's an issue we were always fighting with in terms of what we were doing on GL. So this is kind of a how to transition to Vulkan in 5 easy steps thing. Obviously, this is actually just how we did it, but it's how anyone here who hasn't really done it yet could start off. So first, you really want to research. Obviously, you're doing the right thing by coming here. We spoke to loads of people. We spoke to Crow Team last year and other developers about their usage and whether it mapped onto a sort of GL4 style engine well. Turns out it does, and we'll speak more about that later. Then we picked a game with the D3D11 and a GL4 path for reference. This was super important to us to be able to actually, compare driver bugs, well, not driver bugs, compare our bugs, and compare performance and everything else. So we chose Mad Max for Linux, which we ported maybe a year or two ago to Linux and Mac. We chose the Linux version, obviously, because of Vulkan. And there's another bonus for Mad Max, and there's two actually that I'll mention one later, but one of the bonuses is it wasn't using many of the more advanced features these days. It doesn't actually use compute much. Tessellation's basically missing, which is a big boon for us because on Linux, the open source Mesa driver radv didn't have tessellation support until just recently. So it meant we could ship on that driver and test on it, and everyone was happy. So you want to develop a Vulkan backend. That's a single bullet point, but it's a massive task. Obviously, Alex is going to talk a bit more about that later. We shipped a proof of concept beta on the 30th of March this year, which went really well. With wide driver support. And then you try not to drown the feedback you're going to get from that. We got over 100 emails with great benchmark results, loads of things on a wide variety of hardware, The community kind of getting in touch with us was just brilliant. We had lots of nice conversations about what we could do, so that was good. So getting a bit more into detail about Mad Max. This is a camp in Mad Max. There's a load of camps around the open world. If you played the game, you'll know, but otherwise, it's an open world game, and these are kind of seamless transition camps you go into. Obviously, open world games tend to have a huge amount of dynamic buffer uploads, things like that start hitting performance when you transition to an area with far more detail than the rest of the world, which is just kind of sand and dunes and stuff. So for us, it was an area that had particularly problematic performance. On GL, we struggled a lot. We managed to get it playable and everything else, but it still suffered in these areas, and Tyrant Slash is specifically one that we highlighted. It actually has 4,800 draws per frame on high settings, which is a nightmare, and that's CPU limited in most cases on GL, whether that just is in the driver with the CPU doing as much work as it can, to optimize, as Tom said, but also in terms of, memory bandwidth limited in terms of all those dynamic buffer uploads and everything else. So we really took these camps, and Tyrant Slash especially, as a focus testing for performance improvements in Vulkan. And Alex is going to refer back to this camp a couple of times when talking about certain things we've done. So you get kind of that grounds that. So just getting started, I think some of this is going to be low level, some of this is high level. Here, what you need to know is that Vulkan is significantly different to D3, D11, and GL4, which is the engine really that we're dealing with here. A ton of the work that you always had working in GL in the driver now is moved to you, and you have to do all that work for it, which has some advantages and disadvantages. But the key thing that we want to say is that the porting of an existing engine can be done in stages. I think Crow Team has talked about this before, but really you can get a Vulkan engine working without going too in-depth into all the complicated Vulkan concepts. So you can do an initial implementation without any major engine changes, which is kind of what we've done here. And then later on you can come back and start putting Vulkan concepts within a higher layer within your graphics engine abstraction layer. But obviously, this first implementation isn't going to follow the Vulkan best practices and might fall into some of the traps that is going to come up in that panel discussion later on about worst practices. But it's worth talking about. So I'm going to hand over to Alex, who's going to have a chat about that to you today.
Yep. Okay. I'm Alex, as Mark said. I'm just going to talk about some of the technical details of our Vulkan implementation. So the first thing I'm going to talk about is some things that have been problem areas when going from D3D11 style engine to Vulkan. So the first thing of these is shader resource binding. So firstly, quickly, just give a quick explanation of GL, D3D, and Vulkan differences, just in case anybody isn't familiar with what Vulkan does. So GL D3D, you bind all of your resources to a set of slots, essentially, and then you can arbitrarily just swap them out as you need to, whenever you need to. So then on Vulkan, on the other hand, your resources get organized into descriptor sets. And then shaders refer to their resources by a descriptor set index and then a binding index within that set. And a key thing to note with this is that descriptor sets get recorded separately to the GPU commands. And also that you can't change descriptors while the GPU still might be using them. So what this basically means is that you can't swap out individual resources arbitrarily as you need to. So a sort of ideal usage pattern for Vulkan is you can organize your resources into descriptor sets based on the frequency at which you need to change them. So you could have descriptor sets per object, per material, per camera, etc. And then this allows you basically to swap out all the resource bindings at each level just by a single bind descriptor set command, rather than having to change every resource individually. And then also you can bake your descriptor sets up front, so you can reduce your overhead of things that you have to do at draw time. But yeah, if you've got an existing engine that's based around the D3D binding model, like Mad Max, it's kind of difficult to map this onto Vulkan. So what we did here was initially just started rewrite descriptor sets as we need to per draw. So we have a descriptor set per shader stage, and then just write a new one for, before a draw if either the bound shader has changed or any of the bound resources have changed. And when I first implemented this was something I expected to be like a really terrible area for performance, in terms of CPU overhead. But it's actually not been too bad for us so far. So yeah, to give an example, on the Tyrant/benchmark scene that Mark mentioned, which is kind of worst case for us, we get between like 5 to 7% of CPU times, depending on the driver, spent between allocating, writing, and binding descriptor sets. And also worth noting that the current implementation that we've got that's still doing this is faster than GL, as Mark will talk about a bit more later. But then again, this is definitely not an insignificant amount of time spent doing this, so it's definitely something an area that I want to revisit later on, see if we can do anything better here, like moving towards a sort of like more ideal usage pattern that I described before, and just generally looking for more opportunities where we can just reuse descriptor sets rather than having to regenerate them all the time. So then another thing that's been a problem area for us is hazard tracking. So by this I mean just ensuring the correct ordering of GPU operations, visibility of memory writes, etc. And then, so with D3D and GL, this is mostly handled for you. So in general, things appear to happen in which the order you submit API commands which perform them. And this is because the driver's just all tracking this internally for you and doing whatever it needs to do, like cache flushes, waits, etc., to handle this. But then on the other hand, with Vulkan, it guarantees very little to you about the ordering of operations when memory writes get made visible, etc. So you have to handle this in your application by using the synchronization primitives that the API gives you, like barriers, fences, etc. And then another thing you have to deal with is image layouts. So you have to have your images in an appropriate layout for how you're going to use them at any given point. And then you have to explicitly transition between different layouts, between different usages. And yeah, this is probably one of the trickiest parts of Vulkan to deal with. Certainly for us, it's been like one of the biggest sources of rendering issues while developing our Vulkan support for Mad Max. And these have ranged from things just like blatantly not rendering at all, right down to subtle glitches of things flickering occasionally, things like that. And again, something that's kind of difficult to handle in an existing engine that's targeting D3D11 or GL, because it's just assumed that the driver's handled all of this for you. So the approach we took to handle this was we implemented a system which just automatically keeps track of all of the game's resource usage and then automatically adds in barriers, resource transitions where they're needed. And this is something we at least try to be reasonably smart about doing. So in particular, the system we have, it batches barriers and layout transitions together as much as possible. Because what you really don't want to be doing with barriers is just doing like individual barriers on a per resource basis right just before they're needed. Because this can force the driver to have to do like a lot of unnecessary cache flushing, waiting, things like that. So what a better thing to do would be is to try and batch barriers together into as few barrier commands as you can, because this basically, by specifying a bunch of work to the driver in one go, it can do the minimum work that it needs to do to actually do everything that you've specified to it in that one go. So the advantage of having an automatic system to do this, we can reuse this system across multiple games. So it does, like what we have does a reasonably efficient job of dealing with synchronization, and at the same time this reduces our development effort because it means we don't have to go through like and manually add in barriers and figure out how to do them efficiently and do this for every game that we work on. But then disadvantages of doing this, obviously it will have some CPU side overhead. Because it's what the driver would have been doing internally for you before. We've just moved this overhead from the game side, from the driver side into the game side. But we have at least managed to get this to be reasonably low. So on the Tyrant/benchmark scene, we have like around about 3% of CPU time on the game's rendering threads is spent doing all of like the resource tracking, figuring out the barriers that we need to add. And then Another disadvantage is it turns out to be quite difficult to actually get this right. So I've spent like great deals of time just sifting through render.doc frame captures, trying to step through all the barriers we're putting in, figure out where we've missed some barrier, or missed some little detail of the specification or something. So yeah, despite just having this sort of fairly basic Vulkan port right now, we're still seeing some pretty decent improvements over GL, and Mark will talk about this a bit more later. But at the same time, there's also a lot of scope for us to improve this further as well. And this will be especially the case if we start working with games which are sort of more oriented towards D3D12 and Vulkan ways of doing things. And in both the examples I've just given, there's a bunch of stuff we're still doing at draw time. And there's both cases we could probably do better by moving this work away from draw time, doing more things ahead of time, or just giving more information to our Vulkan backend so that we can reduce the amount of stuff that we're doing at draw time. And this should give us reduced CPU overhead overall. So next thing, I'm going to talk about some best practices. And these are just a few examples of things that we've seen from other Vulkan best practices talks and a few other little details we've picked up while developing our Vulkan support. And these are things even you can just do within the confines of an existing engine that's based around D3D11 or GL. So yeah, first example I'm going to give is memory management. So in Vulkan, memory allocation is decoupled from resource creation. So this means you allocate your memory separately and then bind ranges of your memory allocations to individual resources. And then the responsibility of managing your memory efficiently is moved from the driver into your application. So if you've ever seen any other best practices talks for Vulkan, they've probably already told you this, but in general, do not just allocate memory directly from the driver on an individual per resource basis. Because not only is this going to be slow, on some platforms you also actually get a fairly low limit on the total number of memory allocations you're allowed to make. So any sort of reasonably complex Vulkan application that was doing individual per resource allocations would probably hit these limitations pretty quickly. So what you really want to do is implement a decent memory management system early on. So by this, I mean allocate memory from the driver in large chunks and then just manage this internally yourself. So sub-allocate out of these allocations to individual resources internally. And then another thing that's sort of generally a good idea, just for memory allocations which you make that are host visible, so ones that are directly accessible by the CPU, just persistently map them. And the goal of doing both of these things is avoiding the overhead of the driver, the operating system, as much as possible. Because like the Vulkan calls for doing memory allocation, memory mapping, probably involve like a call into the operating system kernel or something, and you really don't want to be doing this like every time you want to update a buffer or something. And just to emphasize why it's important to do this, some of the largest performance improvements we've made during our development have been from improving our memory management code. So once we first got to the point where we had things running on Vulkan and it was playable, it was performing significantly slower than GL. And the main bottleneck we had was in our memory management code. So over time, we've made quite a lot of improvements in this area. So what we currently have, we have a sort of general purpose memory manager that does basically what I described before. And then just to give an example of one of the performance improvements we've made over time is we now have this fast path for doing dynamic buffer allocations. Because in Mad Max, generally, it does lots and lots of dynamic buffer updates every frame. So what this does, basically, each dynamic buffer has its own internal ring buffer with a bunch of slots of the original buffer size, and then we just cycle between these slots every time the game wants to discard the existing contents of the buffer. And then, because while doing this, you have to make sure you're not going to write over something that's currently in use by the GPU, then we just use a set of per-frame fences to determine when we can reuse slots. And we also use these fences to determine when we can free any resources in general. And then if there's no free slots in the ring buffer, we reallocate it with more slots in it. And basically over time, then it grows to accommodate the maximum size that the game needs to always like have enough space without having to reallocate. So yeah, implementing this path for Mad Max on the Tyrant Slash benchmark, it gave us around about average 15% frame time reduction over just using our general purpose memory allocation code. So this is like something that's it's certainly worth implementing something like this if you have a lot of dynamic buffer updates going on. And this is just like an example of how Vulkan gives you the flexibility to tailor things to your specific application. And you can do this both to increase performance and reduce your VRAM usage. So there's a bunch of features that the API gives you, like memory aliasing, for instance. And these just give you lots of flexibility to really tailor your memory management to what you need for your application. And then another thing you have to be aware of is you do need to make sure you handle sort of differences between different hardware vendors and different drivers in some places. So you should start testing your Vulkan code on different hardware vendors pretty early on, so you can make sure you can handle all of these differences and try to do the optimal thing for each driver. And with this, I'm not necessarily talking about implementing like vastly different code paths for each driver. We just have like a bunch of small places where we do a few things a little bit differently depending on what hardware we're running on. So yeah, a big example of this is with memory management. So the memory management setup that the driver gives you, like the memory heaps and memory types that you have available to make your allocations from, can vary quite a bit between different vendors and drivers. And code that works like against one driver might not necessarily work or be the most optimal thing to do on another. So you have, just an example of this, like when I first implemented our memory management support, I did it against Nvidia's driver, and then the first time I went to run it on AMD and Intel, it basically didn't work properly because it wasn't handling like all of the memory types properly. And then once it was working, it wasn't necessarily using the most optimal memory types everywhere. So it's a specific example of how you get different memory types and what may or may not be optimal. On AMD drivers, you get a memory type which is both device local and host visible. So this means it's VRAM, essentially, that's directly accessible by the CPU. And then on Nvidia's driver, you don't get this. But this is like a really good type to use if it's available for dynamic buffers, because it means you can just write directly into those buffers without having to have the GPU reading over the PCI Express to system memory or having to have separate transfer commands all the time. And then beyond this, there's also some vendor-specific extensions which can be useful both for getting access to hardware features or for performance. So the main example we've seen of this performance-wise is that Nvidia have this dedicated allocation extension. So what this basically allows is to mark a memory allocation as dedicated to a single resource, which does kind of go against sort of the memory management best practices I described before of like sub-allocating out of allocations to individual resources. But it's mainly intended for use for render targets and other large resources. And this sort of allows the driver to enable various hardware optimizations like render target compression that it can't necessarily do on normal Vulkan memory allocations. And yeah, an example of this, a GPU limited scene we had in Mad Max, after enabling this extension for the render targets, it saved us around like 15% GPU memory bandwidth, and that translated into around about 7% average frame time reduction. So certainly worth enabling this extension if you're going to target NVIDIA hardware. And then beyond this, there's a bunch of other extensions for vendor-specific features that you can use that may be useful as well. So that's all I have. I'm going to pass back to Mark now, who's going to talk about some of the performance gains that we've had going from GL to Vulkan.
Thanks, Alex. So yeah, coming back to Tyrant Slash, I think the key part here is, in general, not even for just for Tyrant Slash, we're going faster than GL even with a rudimentary approach on most hardware. And obviously, a lot of this talk is about CPU side gains, but those were the main problems we had with GL in the first place. And the workload is being saved a lot by doing basically a specialized version of the driver's work. And the key thing to note is that now, in these situations, specifically Tyrant Slash, we're now managing to keep the GPU busy almost the entire time, which is a very big plus on our part. We like that a lot. So just a quick thing. These graphs are on Linux, obviously. They might not apply to Windows or Android. But this is an example. We had 4 kind of benchmark scenes. If you want to have a chat about them, you can at lunch. TL is the Tyrant Slash one. And this is just a delta FPS graph with the middle line being 50%. So you can see on like a 916 and 1070, we're getting over 50% on delta FPS, which means 50% on frame time, which is a quite considerable gain on GL. And it's basically across the board. That 1050 Ti bench I realized yesterday was on a lower end CPU, so I can't remove that now. But either way, the gains are pretty damn significant. On AMD on Linux, it's kind of weirder situation. It always has been. Hopefully it should be smoothed out soon. But the 2 blue graphs here are Mesa, which is the open source AMD drive, or the open source driver on Linux. And you can see actually GL is faster on that driver. But that's kind of because at the moment that driver just hit 4.5, and they're just going through a load of performance updates, which is really banging Mad Max up in the charts. And the Mesa Vulkan driver, RADV, isn't even Khronos certified yet. Even it actually prints F telling you that it's a debug driver. But as you can see, it's actually competitive with the GPU Pro driver, which is the closed source AMD provided driver. And they're both pretty much competitive. And we think that's amazing. We think RADV going forward should be getting faster and faster. And we're a big fan of open source drivers on Linux. Alex has done over 10 commits into them. I've done a couple to try and help that. I think we've got a couple of Mesa people here, so thanks. But yeah. So kind of in summary, on Linux especially, we've already got wide support. That's Nvidia, AMD, Intel, and Mesa as well. We've only had to drop some older Intel chips, Haswell specifically, but there's features on Haswell that are missing hardware-wise that just, it wouldn't really have run Mad Max anyway, so we're not that not bothered. Open source driver support on Linux is coming along really well. We're really pleased with RADV. It's just been adopted by SteamOS as well, which for us is a big bonus. And yeah, RADV is definitely as competitive, and in some games, some of the upcoming things we're working on, RADV is faster already, even before full certification, so we're really happy with that. And Vulkan in general is way further along than we expected this early on, internally and externally. Externally because the drivers are, as stable as GL already on Linux. Maybe four years ago when we started, the GL drivers on Linux were taking down your machine all the time and everything else. We kind of expected that with Vulkan, but it's not there mostly. There's a couple, but that's standard. It's really as stable as GL already, which is brilliant. And as we've kind of said, this is a preliminary implementation. We're really happy that there's so many avenues for improvement that we know of already. There's like a technical debt list of like, we can improve here, we can improve here, and we can improve there. And because we have the control with Vulkan, we can do that, which is great. So going forward, we're going to be using Vulkan on pretty much all of our Linux ports. Some maybe not, but we know we launch maybe 4 or 5 ports a year, so that's 4 or 5 Vulkan games sometimes coming out, which is pretty good. And because we're here at ARM, we're also on Twitter, probably like around about now, announcing that we're going to be porting Grid Autosport, the full game and everything, to Android on Vulkan. So if you want to come have a chat about that, come have a chat about that as well. So you might be the first people to hear that if the Twitter stuff hasn't gone out already. So yeah, basically, get in touch with us if you're working with an IHV and you haven't got in touch with already. We want to talk about stuff. If you're a driver programmer, especially on Mesa, we give free keys of all our games and future games. Basically, it's just a key to feral games to Mesa developers, the open source driver on Linux. So come and have a chat, because we have some test cases for you. And if you know LLVM, like the back of your hands, Mesa's backend for its shader compiling is now LVM, and we're looking for people who know that really well to help optimize it. So we'll have the game Mad Max running at lunch. We'll also have Dawn of War 3, which is coming out next month, which is running on Vulkan over there as well to have a chat. And yeah, I think if we have time, I think we've got time for questions. Alex, you want to come around?
Yeah.
I really should let other people ask questions first, but nobody's holding up their hand.
Sure.
So, sorry, it was Alex said that your experience was that a fairly naive descriptor set management approach worked pretty well, which is great. And we hoped that allocating and freeing, particularly ring buffer access, using reset descriptor sets, would be efficient, and so I'm glad to hear it. I was wondering about descriptor pool management, if that was how you did it, and was it easy, or did you have problems sizing the pools, and generally what was it like?
Yeah, so we have, basically what we do for descriptor pools is we basically just do, because we're reallocating descriptor sets all the time, we have basically a set of per frame descriptor pools that we just do reset at the beginning of each frame once a frame's finished, and reuse it. So what we do have is we basically, at the moment, just we sort of allocate new pools with with fixed amounts of descriptors, pretty much. So they're kind of like arbitrary choices, sort of like tuned a bit, but it's mostly just sort of arbitrarily sized pools. So yeah, and then once a pool's run out, we keep track of how many descriptors we're using internally, and then if a pool's empty, then we allocate another one, and then just leave those allocated over time. So eventually we grow to the size that the game will need. But yeah, it's still sort of some just arbitrary choice of the sizing of pools, which I don't know. Maybe we could tune that a bit better, but I don't know.
Stunned everyone into silence.
So is the game GPU limited after all, at this point?
For the most part, yes.
Cool.
Yeah, in fact, in most cases we were, in a lot of cases in the game in general, we were CPU limited on GL.
Especially the camp
Especially
areas,
the camps.
because they've got so much draw calls, buffer updates going on, that sort of thing. Outside, when you're driving around in the open world sort of areas, they were sort of reasonably GPU limited on GL, but now it's, for the most part, on Vulkan, we're just mostly GPU limited everywhere, depending on the hardware you're running on, of course.
I was wondering, were you able to use any of the multi-threading abilities in Vulkan with your ports?
We haven't explored that much so far, just because this is a sort of D3D11 level engine that wasn't really doing any sort of multi-threading internally. So yeah, if we try and do Vulkan support for games which are doing that sort of thing, we will definitely look at doing it. But just because we're doing ports from Windows games, essentially we're somewhat constrained by what the original game is doing. But yeah, it's certainly something we'd want to look into in future, because obviously that's one of the major things that you get from Vulkan, is the better multi-threading capabilities.
Last chance.
So if you were porting from D3D, I assume all the shaders were in HLSL. How did you deal with that in a Vulkan port?
So we already have mechanisms for dealing with that, because obviously we used to be porting to OpenGL. So we're basically using the same system, really, because we translate to GLSL basically, and then go from there to SPIR-V. In fact, at the moment we're doing a lot of it at runtime where we could pull it off. But
yeah, that's certainly something I want to look at later, because it's basically was just taking our existing GL to GLSL translator and doing that at runtime. So yeah, I want to look at maybe going direct to SPIR-V instead, and then caching those, so we're not doing the translations at runtime.
Yeah, if you play the Mad Max Vulkan port, it does stutter a little bit at first, into a few scenes and things, because we still are doing a lot of work at runtime to sort it out. But that's, again, one of those areas for improvement that we're talking about that seem like is easily an avenue for investigation, basically.
Alrighty. Oh, Tom again. He's trying to make me run, aren't you?
So you got to understand, I'm absolutely fascinated with how real programmers use this stuff, because we put things into the API based on input, but still without a real deep understanding. So one thing I'm wondering about is parallel command buffer generation. Have you tried it? Do you think you need it? Do you have any experience with it?
We haven't tried it yet, but yes, we definitely will want to do that at some point.
Yeah.
Thanks.
None in the opposite corner. Cool. Thanks again. So no further questions. Thank you, Mark and Alex.